Hi, I'm going to talk today about a beam of light, probably of multiple colors. That would be good, maybe white light, which is impinging on a thin film. And I've drawn the film a little bit thicker than it really is because we're going to talk about how we get destructive interference in that film if we set up the film with an index of refraction smaller than the film's index of refraction and bigger than the background. So this film is said to be on water. The index of refraction of water is 1.33. The index of refraction of air is 1.00, and the index of refraction of the film is 1.46. When we look at this, we find that there's destructive interference occurring at 520. Now, destructive interference occurring at 520 could be anywhere along the various angles, but it turns out that what we want to do is we want to find the minimum distance at which we can see this destructive interference. Keep that in mind. Secondly, keep in mind the fact that we're going from a smaller index of refraction, according to Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. And that indicates that there's a phase change here and a phase change here. Therefore, these beams, if they're not interfered with down here, will just reflect off this top surface. 520, though, is absent. That means it's dark. There's a line, there's an absorption line there. Interference implies the optical path length of the film is lambda over 2. Optical path length is on those diagonals, and so we have to throw in a cosine of theta in order to measure the distance d, which is the distance straight up and down. For the shortest minimum thickness, the distance we are working with has no overtones. And so let's set up the general equation for interference, and we generally say that this is m lambda equals 2 n film, meaning the index of refraction of the film, times the distance across the film, which is the thickness of the film, times cosine of theta 2. And we said that we don't want overtones, so m is equal to 1. We also note that in order to get the shortest distance, cosine of theta 2 has to equal 1 to make the total equal to the lambda 520. So what happens is we know this is a minimum because there's only one set of destructive phase change. And if the water had a different index of refraction, we might get 2, and this equation might change by a little bit. This lambda is equal to 2 times the index of refraction of the film times the distance. The distance, therefore, is 178 nanometers.